everybody, and welcome to Live from the Lab. In this show, we are going to talk about what is XRF. Actually, let me clear that up a little bit for you. All right, so what is XRF? So what is XRF? Well, XRF stands for X-ray fluorescence microscopy, or not microscopy, X-ray fluorescence spectroscopy. And it is used in order to quantify the elemental composition of things. So when we think about it, the way I like to think about it is, say that we're making a cake. And in that cake, you might put flour and sugar and things like that. Now XRD, that could tell you, oh yeah, this is flour and sugar. What XRF would tell you is that you have carbon and hydrogens and those types of elements. And that will give you the overall elemental composition. And so XRF is a very important point of the analytical toolkit in order to determine actually what is present. So in order to learn this a little bit more, what we've done is we've put together a video.
What is XRF? How does it work? And what is it used for? X-ray fluorescence, or XRF, is a reliable method for determining the elemental makeup of any material, as well as determining the quantity of each material. Modern XRF instruments are easy to use, are non-destructive, and can measure a material with little to no sample prep. This makes XRF a preferred analysis method for a great number of industries, including mining, petrochemical, metals, cement, food and beverage, and R&D. An XRF experiment begins by irradiating a sample material with X-rays from an X-ray source. Every material is made up of many atoms, and each atom has a positively charged nucleus surrounded by a cloud of negatively charged electrons. The electrons orbit the nucleus on distinct energy levels or shells. When X-rays encounter an atom, they're absorbed by the electrons orbiting the nucleus. If the energy from an incoming X-ray is high enough, the electron receiving the X-ray will be released from the atom. An empty electron spot close to the nucleus is not a stable state for an atom, so it will pull an electron from a farther away shell to fill that spot. When this happens, a new X-ray is emitted as an X-ray fluorescence photon, which is unique for each element. The energy shells from an atom are named alphabetically, with the closest ring being K, then L, M, and so on. This atomic structure is described by the familiar Bohr model. The photons emitted from these shells were originally described in a notation by a physicist named Carl Mané-Siegbahn. Appropriately, this is known today as the Siegbahn notation. So when you hear the characteristic lines of elements referred to as K lines and L lines, or K alpha and K beta, you now understand that it all refers back to these two models. By applying the Siegbahn notation, we stated earlier that XRF can not only determine which elements are in the material, but also determine the quantity. The key factors to measuring the fluorescence relies on a careful balance between the instrument's power, sensitivity, and the ability to resolve the data. Each element emits a unique fluorescence. There are two techniques used to separate and identify these energies. The first method is known as energy dispersive, or EDXRF. The spectral resolution in EDXRF is achieved by the quality of the detector. These detectors have several thousand channels to simultaneously measure the entire spectrum coming off the sample. The more channels, the better the resolution. Because all radiation from the sample is collected directly after the sample, the power of these systems can be lower. This makes EDXRF perfect for benchtop systems and low-intensity setups like micro-XRF or handheld XRF. In wavelength dispersive, or WD-XRF techniques, Bragg's law is applied to determine at what angle these characteristic X-rays will be located. Filters are used to improve the background of spectral results, collimators are used to make a parallel beam coming off the sample, and crystals with known lattice parameters separate the wavelength related to an element of interest. The detector is positioned at 2 theta to measure the specific elemental wavelength. Placing all of these components between the signal coming off the sample and the detector comes at a cost. The intensity reaching the detector is diminished significantly. Therefore, WDXRF X-ray sources must be much more powerful. WDXRF usually has better resolution than EDXRF, especially for the most common elements, which is mostly needed for advanced applications. Due to the higher power, WDXRF is also capable of measuring light elements that naturally have very low fluorescence yield and cannot be easily detected using EDXRF. But remember, EDXRF systems have far fewer components and lower power requirements. So if you're looking for a fast, broad, and less expensive way to determine the elemental makeup of your sample, EDXRF provides an ideal solution. So how do we get from detecting the elements from the spectrum to quantifying them. XRF spectrometers not only determine the presence of elements, but also the amount of them in a sample. This happens by setting up a calibration. Standards with known concentrations of a material, for example, cement, are measured, and the intensity is plotted versus the concentration. A regression curve is fitted, and thanks to modern software, can be optimized to improve the calibration. When an unknown cement sample is measured, the intensity is compared to the calibration curve of the standard. This sort of calibration can be set up for a wide variety of materials like petroleums, polymers, metals, and so on. Modern systems offer semi-quantitative solutions, which can analyze the material without those standards. In other words, they're standardless methods. XRF is a versatile solution that can analyze any material, from solids to liquids, loose powders, or pressed powders. For most elements, XRF's analytical dynamic range is from parts per million to 100%. And thanks to WD and ED XRF techniques, these instruments are suitable for an increasingly wider range of applications and budgets.
All right, everybody, welcome over to the other part of our studio. So we had a little bit of mishap there. The door was open, but we got it closed. So this is live from the lab, and this is the show where we talk about different technologies that we use in order to study the world around us here at Bruker. Now today I am joined by Julia.
Hey, John.
And she is our expert in X-ray fluorescence.
Thank you.
Spectrometry.
Spectrometry.
Okay.
People say spectroscopy, but that's only the qualitative part because you see, right?
Yes. Yeah.
Scope, Greek, from seeing, whereas we actually measure how much is in something, so it's spectrometry.
Now you've been doing XRF for quite a long time, huh?
Yeah, like 10, 15 years.
Yeah. So what makes it like your favorite thing?
Honestly?
It's not your favorite thing.
No, it is my favorite thing. No, that's what my daughter would say. It's not my favorite. No, I do like it because it's really cool that you can basically put anything in the machine.
Yeah.
And you get a spectrum and you can at least see what's in it. And if you tell the machine enough information, you can either get an educated guess what's in it, or you can get precise down to ppm levels. And I really like in the video how it explained the XRF principle, that there is a source, a sample, and then the rest that happens is in the part of the detection. And we wanted to make sure that people understand, like on the atomic level, where the X-rays come from, and why they are called K alpha, K beta, M alpha, whatever. Because when you get an X-ray machine, right, you get all of these informations, and we want to make sure that we have something that people can watch and get like a really cute, fun overlook.
And it's kind of interesting too, because when like people hear X-ray, right? You normally hear X-ray. I think the first thing that comes to mind is, like, say you're at the airport and they're checking your bag, like that they're trying to just visualize what's in it. But here we're talking about something different. We're talking about using those X-rays, but to get the elemental composition.
Right. We're looking at bulk composition. Right.
Yeah.
We're not doing the X-ray part, looking through things and seeing the dimensions. We also look through things, but for a different purpose.
Yep. And those are typically much higher energy.
Yes, that's true.
Machines. So this one is a lower energy, but that's what gets us that composition.
Right.
So machines have changed quite a bit, though, over time, right? I mean, I kind of remember back in the day, I can say that back in the day, these machines, they were so huge, and the generator itself actually would have been like even bigger than this machine here, the whole machine.
For the larger WD systems, For the EDXRF system, well, it depends on how far you go back.
Yeah.
I don't know how far you want to go back.
No, I mean, no, I mean, I think out there, sometimes the perception is that you have to have this huge facility and stuff. The reality is that you've got everything from the larger WDs these days, right?
True.
On the other end of the spectrum, you got handhelds.
Yes.
And then here, kind of in that happy middle spot, you got the benchtops these days. Huh?
That's right. We also have benchtops WDXRF. So we did an S6 Jaguar special I don't want to say a few months because it's been several months. But that was the last time when we talked about XRF together.
I think that was in our old studio. So.
Yes,
yeah.
So I think that's also kind of interesting. The difference between WD and EDXRF, right, is the resolution, and that comes from in EDXRF, you only have the detector, right? As good as your detector is, that's as good as your resolution is. Whereas in WD, If you have a certain type of component, you can increase your resolution.
Okay.
Sure, there's limits to it, but as long as R&D keeps researching and figuring out maybe better crystals, there is still room for improvement.
So, and that's that key differential, right? If you're looking just more in the scheme of, I don't necessarily know what I have, or I could have a huge range of things, it's not the same thing every day,
That's right.
ED might be a little bit better for you.
Yes, and ED also gives you the whole spectrum right away, whereas WD, I mean, if you use a standardless method, you also get a full spectrum.
Okay.
But WD is, it's more precise, right? It has better resolution, has higher power, and it's very good for these routine operations if you want to get something quickly. And on the other hand, what EDXRF cannot do, WD with the higher power can measure light elements. And by light elements, I'm talking fluorine, carbon, even down to beryllium.
All right.
EDXRF can starting to scratch on those levels, but at this point, we can measure it, we can detect it. The quantification is still hard because you need to have very good standards. You need to have a very good idea of what else is there, because in EDXRF you have a lot of overlaps there of these lines that we just talked about with the Bohr model, right?
Yeah, yeah. So now this right here, this happens to be a Puma. All of the machines are named after cats, right?
It's more and more relatable.
So the Puma here, that's true, it's relatable. And it's really nice. It just kind of hangs out, does its thing.
That's right.
So just like a cat. So the Puma now, what kind of machine is this? Is this the WD or is this the ED?
That's the EDXRF system.
Okay.
And we just recently, well, not recently, but a few years ago, we brought out the Series 2 with a better detector.
Yeah.
So this machine I brought into the studio because I wanted to show you how quickly you can measure something.
Yep.
They come with a touchscreen, and maybe we can show the touchscreen. So I'm going to show you how you can measure something.
Sweet.
So I think because it's Christmas, I brought more Christmas or holiday related samples. I think we can all extrapolate that to real examples.
Yes.
But I have, so one thing I have is a gold necklace, or at least I think it's gold, right? I got this years ago. It's I forgot to string it back on, but it's a little dolphin, and it's the necklace. And I'm going to put everything into a little cup, right? It's we call it a liquid cup or a powder cup, but that's you can also put something like this in there. Okay?
So you don't have to say melt it down, grind it down, make it perfectly flat.
I mean, you can, but you're not going to do this to this.
Right.
No.
But you don't have to.
No,
if you didn't want to. Okay.
Also, we would have a problem, John, if you would make me do that.
All right, so down here it looks like we have a pretty big sample changer.
Yes,
then.
and we also have, I'm going to talk about this later while this is running, but yes, you can put 22 samples in there, and you can take the tray of the 20 samples out and can take that in the lab with you.
And this is compatible with some of the other machines we sell,
of course, because if you want to have two or if you want to have one as a backup, then it's nice to be able to move things back and forth, right?
Does this one work with the XRD machines too, this tray?
Actually, I'm not 100% sure.
We're not 100% sure. We didn't.
But the sample size is the same.
Okay.
Yeah.
All right.
Let's look at the touch screen, right? I want to show you how you can set up a sample. So I placed this here in B1, and we can see that here on the screen. Oops.
Okay.
And then we're going to measure it with our standardless method. We'll call them smart, because why not? If I use the mouse, it doesn't like it as much with adding a... We're just going to give it some kind of name, because I can't see that well without glasses.
Yeah. But you can also touch the button.
I can touch the button, but that would look really weird if I'm going to turn around during the live. So, right, we know this is a solid. We're just going to say it's infinitely thick.
Yep.
Going to go to the next one, and because it is metal, right?
Yes.
Whatever it is, it's not going to be aluminum or sodium. So we can measure this in air. So I'm just going to click next here, and we actually played around with the machine a little bit so that we can keep it open while it's going to pick up the sample, right? So you can see the sample handler comes over, picks it up, magnetic, and then it brings it into the machine over there.
All right.
Opens the lid, and it brings it in. And then the cool thing is, right, because EDXRF measures the spectrum the whole time, and at all times it just accumulates counts, we can actually look at the spectrum while it's taking it.
All right.
For that, we need to look back at the touch screen, although we have a little bit of time. Because
So in terms of the touch screen, then I
Yes.
guess what we're seeing is that we have a picture of the sample
yes, we have
area.
a virtual version of the loader.
Okay.
And then on the bottom right, we have these like
Yep.
very self-explanatory buttons: start, stop,
Yep.
delete what's okay. Up here, I have a check sample that
Okay.
we run, and because we're also scientists, we're live from the lab, we're doing due diligence, and we're
Yep.
running our check samples before we use a machine. right?
Okay.
But it also shows you can have different colors
Uh-huh.
if you want to set this up. So this is the touchscreen version, so it's easier and more, how do you say that? Like you have buttons that you can push, right? You can start a
A
new
little more
session.
user-friendly.
Right, but if you have a mouse and a keyboard,
Yep.
right, you can have an external PC as well.
Okay.
But while we're running this, right, we can go and look at the live spectrum here. And we can see, I already prepared that. We can add the lines in there. But what we see is, yes, there's copper in it, and there's also
Okay.
gold in it. And it looks like there's more copper in it. But that just is when you look at just the spectrum. But we
Yep.
have a K alpha line here and an L alpha line here from the
Okay.
gold, right?
Yeah.
And L lines do not fluoresce as much as K lines. So actually, we have a lot more gold in this than
All
copper.
right.
But those are the things that you learn when you do this for 10, 15 years.
Yep.
Or maybe just 2 or 3 months. But
Is this one of those things though where like you look at it like you're doing it and you're just kind of getting that like a qualitative estimate, or can you actually get quantitative
you
numbers?
can get quantitative for this one too.
Yeah.
Let's go back and look at the real simple result. Oh, we still have a few more minutes, seconds to go on this one.
So now, how long does a measurement normally take? Is this representative? Maybe we sped it up a little bit.
We did speed it up a little bit, but it is still representative. I have
Okay.
measured samples. I have set up calibrations that took about 1.5 minutes, where
Yeah.
we just do one sequence pretty briefly, just two
Yeah.
elements, and they were all in the same range that we wanted to look at. Because EDXRF might look at different ranges with a filter, without a filter. Oh,
Yeah.
we just saw the X-rays turn off, right?
Okay.
So that it can open the chamber again. Yeah, and so 1.5 minutes is still possible. And while it picks it up and takes it out, we will see that it, in the background, will do some evaluation. What did it come up with? Yeah, gold about 60%, copper about 30%, and a little bit of zinc in there.
Okay.
So that is 58%, that is 14 karat gold, just like my uncle said, so thank you.
Hey, there you go. So
was
it's
a
not
really
just
nice
like
gift.
a titanium nitride type coating.
Nope,
It's
it's not.
real gold.
Why do you say it like that? It's,
What?
Of course it's real gold.
Yeah. No, I'm just saying, here on Live from the Lab, we found real gold.
That's true. But
Okay.
yes, you can imagine, right, with these peaks, you can extrapolate that.
Yeah,
If you want to
yeah.
mine for gold or copper, right, the peaks will
Yep.
be there as well. It's not like there would be somewhere else, but they might be smaller and there might be
Yep.
other elements around it. So if you want to measure something like that, depending on how many elements of interest are there,
Yep.
how convoluted it is, you might want to go to a WD system, and you might want to set up a calibration.
So the benefit, though, of one of these machines is that it's going to be less expensive, take up less room. It still has that sample changer. So, for example, if this was your thing, you were doing scrap stuff, you can actually throw, bam, 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 all the samples in, walk away, come back, there's your data.
We routinely work with our colleagues in XRD if they have like some compound that they can't figure out what it is. They ask us to measure it, and then we can define, is that element that they might think is there really there or not? And because we can get to lower levels of detection than they can.
Yeah, and that's the big thing with any analytical technique.
Yes.
You know, I don't care if anybody out there is trying to, like, you know, you're in the market for a machine and somebody comes to you and says, this is the end all. This one technique will give you everything. I'd run away from that, because the reality is that each one is a piece of the puzzle.
That's right.
Some pieces are a little bit more important. Some of them are auxiliary, but every piece gives you the more clear picture of what's going on.
Correct.
Yeah. So like you said, I mean, for XRD, that's a little bit more my background. To me, that elemental information, that is so key to validating and oftentimes even getting a good search match.
Yes.
Because you can exclude so
Definitely.
much
Yeah.
of the database there. So, I mean, metals, like you said, man, they fluoresce like crazy. That's kind of easy.
Yes.
That's kind of the softball thing
Yeah.
here. I think you brought another sample a little bit more challenging,
I
right?
did. And again, because it's Christmas time,
Yep.
although I did modify it a little bit, I made cookies.
Okay.
I made chocolate chip cookies because
Yep.
I can also buy chocolate chip cookies, and I wanted to show if there's a difference between the store-bought ones and the ones that I made.
All right.
So-
All right. Are we going to post your recipe? No.
Yes, we can. It's very simple.
There we go.
But what I want to show you is, first of all, the easy sample prep. All we had to do was cut them into the right shape, right? There's nothing else. They're flat on the bottom because they were on the baking sheet.
Yep.
But we also can see, I mean, I'm not sure if you can see this, but the store-bought ones are the ones that have the same height, right? I made one that's a little darker than the other ones because
Yeah.
I've got
I mean, I guess
burnt.
here we can.
Yeah, we can show.
We could pick them
the
up and maybe
difference.
show.
I'm gonna show them closer.
So like these
Okay.
are the. I've got the store ones.
Yes, I have the non-store ones.
So yeah, that one's a little bit bumpier on the top.
Yes, and this one is not so thick,
Yep.
right? You can see that one
Yep.
is.
So and then the
flatter.
bottoms. Yeah, here we've got kind of that very industrial look. I'd call it almost.
Yes, I
right?
would say so too. This
And then
one
we
has a
have
little
that-
bit of a chocolate chunk in it.
Yeah, it's that craft look to it.
Correct.
We would call it, right?
Yes.
Okay, so we'll put these back.
And so I measured these beforehand.
Yeah.
If we wanted to measure them, again, we would just set it up, would say, go here.
Yep.
We want to measure probably also elements. Or we can do it with, I think I measured them as organic just to get an idea, but it doesn't really matter.
Yeah.
And the point that I want to make here right now is just looking at it.
Now I see this little barcode sign
Yes.
next to that sample ID. Does that mean you can hook up like a
You can
barcode
hook up
scanner?
a barcode. Yes.
Oh wow,
Yes.
that makes it really
This
nice.
is also a solid sample. And we're going to measure it in vacuum because it's not crumbling.
What would the benefit of those other modes? Because I saw like helium.
The helium is for if you want to measure powder or liquids.
Okay.
Because you can imagine what happens if you put a powder in vacuum. It goes,
Yep.
right?
So that would like kind of flush
Yes.
that little sample area. That's
But only the
closer.
sample measuring area, right?
Okay.
When we talk about WDXRF, that's
Yep.
very important because WDXRF with all of those things in the beam path, that's always on a vacuum, and we only flush the sample measurement chamber.
Okay.
So this is running. We can stop it in between. There's
Yep.
not that much because I already prepared this. Like,
Hey, here we go.
Like a good
well,
show.
Okay, then speaking of that, just for everybody out there, we had the necklace thing. It's kind of
Yeah.
that gold, going to shine
Right.
a lot. If you were presented a sample like that, here we did 1.5 minutes. What would you, or I don't know if it was 1.5, but what would you recommend? Somebody say, hey, I'm looking at this. What's that realistic number? This is how long I'd recommend
Probably
running
around 7 minutes.
it. 7 minutes.
Yes.
If you were
for
pres-
this one? No,
Yeah,
no.
the
The 1-2
gold one.
minutes. Yeah,
1 or 2 minutes for the gold, and then for the cookie,
I would do like 7 minutes.
about 7
or so.
minutes. Wow, it's still.
It's
I mean,
almost
that's
as
very
long as
very
it takes
fast.
to bake them. 8 to 10
That's
minutes.
That's true. You could create like a feedback cycle where you make it and then you for the
Yes.
next batch.
Yeah, but I didn't bring the cookies because it's Christmas. I also brought it because one of the newer applications we do is going into the food and feed market,
Yeah.
like looking at feed for animals, right? And so you
Yes.
can measure this
Yep.
and you can see what's in there. And I think for industry that's interesting. And I think what's interesting also is even with the cookies, without sample prep,
Yep.
without anything, we could already see some things. And I want to show that to you on my laptop that I brought to you because the laptop has the
whole
more
picture.
intricate
All right,
version
all right,
of the
here we go.
software, right? So what we can see here is no mouse, wrong mouse.
Too many mice here.
Too many mice, yeah. So I have one, that is the industrial one.
Yep.
It's K1 and K2. And what we can see is that it overlaps totally, right? There's K1, I measured
Yeah.
everything twice. They are totally overlapping. They're
So
exactly
it's going to
the
be
same.
the same
One
every
cookie
time.
is the same thing.
Yep.
And the other thing is, the ones that I made, they are a little different. Maybe the difference is the chocolate chip, who knows?
Yeah.
One thing that we can see though, that the industrial one has more salt in it, right? More sodium.
Yeah.
And my cookies do not have that much sodium.
Hey, that's a really important point. I mean, a lot of people have sensitivities to this, so it's important to understand. Two
Right.
chocolate chip cookies, they're not the same, right?
So XRF also is a very good just R&D technique, because right,
Yeah.
is this the end of all? No. If we wanted to really compare these, we would have to make sure that they're prepared the same way. So we probably would have to grind them down, and then we would have to press them, and maybe make sure that we take out the chocolate chips,
Yeah.
right? Things
Yeah.
like that. But on the other hand, if we just want to have an overview, this is great, right?
Yeah.
Full
Yeah.
spectrum right away. I didn't mention this, but here in the middle we can see our we can see the tube lines, and that's what I mentioned before. There could be a filter in it, so we can take those out, the tube lines, if my software listens to me, right? And then we can see down here, yes, the potassium is really here, and we take out, we filter out those lines that come from the tube.
So like what kind of tube does this use? So an
this one is a silver tube.
Silver?
Yes.
Okay, and then like what voltage, like what power do you run these things at?
This one is 50 watt.
Yep.
And the software gives you different options of how you can run it. So you can go full power, you can have something that just tests to go full power, you can have it at lower power, things like that.
Okay, so yeah, in XRD, we're kind of using that really characteristic peak. Of the, say, copper, that's 8 kilovolts. But here we really want to just use a very, very high energy to get that excitation.
Correct.
That's the
and with EDXRF, it's not so much, but you know, WDXRF uses the same principle as you do, right? But instead of looking, I think I'm repeating myself here, but instead of looking at the crystal and wanting to know the 2D, we want to know what goes into the crystal because we do know the structure of it.
Yeah. So it's just kind of reversing Bragg's law there, right?
Correct.
Yep. XRD, we know lambda. We're looking for D.
We don't know lambda.
WD, don't know lambda, but we do know D. So that's a great setup. Okay, so this thing, I mean, pretty easy to use. By the way, one other feature out there that I really like is that you can actually change the angle of the screen, right? So there's a lot of usability stuff there. Even setting it up for for our little demo today was nice because there's like HDMI cable in the back, so if you wanted to go to a screen, that's really easy to do. So it's a really, really easy to use instrument, I think.
I think so too. I think it's great. And yes, I know the resolution is different, but you get a lot of value out of it, right? And the possibility of seeing the whole spectrum alone is fantastic because you can pinpoint things right away.
And in terms of then, like for people out there, if they're just getting into XRF, maybe they have another tech that they use though. You do like kind of demos and like. I don't want to say consultation. It's almost like a scientific consultation, where they can come in and say, I have this problem.
Yes.
Can you help me? Right.
We do that. Depending on what a customer wants, right? They can send in samples. They can come and visit us. We have a new lab. Oh no, we don't have a new lab, but we like renovated it. We put it. We renovated it. We put some more machines in. And yes, people can come. People can visit. We do virtual demos where we put a camera in the lab and we show them how the samples were run. We write reports that you will get afterwards. So we try to give people information before they buy the machine. Right? And I want to make sure that they have all the information, right? Just like as I said before with the light elements on EDXRF, always make sure you test that before you just buy the marketing. And with your experience, you know, if somebody says, hey, this is a problem I have, I mean, you're able to say, you know what, EDXRF, that's going to solve it, or WD, or this machine. And then on top of that, you can get some sample results, like you said, see it in person. We have the capability of doing kind of virtual demos too, video demos, so if anybody ever has a question, just reach out to us. And there's also like Julia's around the world. Well, I'm not going to say there's Julia around the world, but there's other application scientists we have all over. And we are in close contact with them. So also for global companies, that's really nice because they can talk to my colleague in the UK, and then I talk to their colleagues in the US. So it's helpful.
And with kind of a technique too that's used industrially, it's important to know that there's a certain backing to it, right? And so we've got a whole service organization too.
Correct.
That'll get you taken care of. All right, so with that, we're going to switch over and answer some questions. Now, if anybody who's joining live right now has questions, you can go ahead and write them into your YouTube window, and we will answer them immediately. Otherwise, if either you're watching this later or you think about something later, you can always send them in to live.events@bruker.com, and we will get to answering them. But the first questions that have come in, the first one is from Mia, and that is, what is the elemental range? Particularly, what about light elements?
So the elemental range is always sodium up to americium, or sodium up to uranium. And then the light elements, I would always recommend to go with the WD system because that's where you have higher power, you can have the right crystals. You can go to fluorine, and you can even see carbon with this one. But as I said, if you want to quantify it, you have to have higher levels of it. And you should definitely have your set of samples ready and do a proof of principle measurement with us. And we would love to support you with that. Because I don't want to like recommend something that I haven't tested out or where I don't know what the outcome is.
Yeah, no, I mean, it's interesting. It's amazing the diversity of things, though, that you have experience with. So sometimes
I think
you do
that's
have.
cool.
Yeah,
I really like
away.
that I can apply what I learned before and like go into these different industries like cement, metal, feed and food. Right? It couldn't be farther apart, but it's all connected at how they measure things.
Yeah, you never know what's going to be next. So the next question, what about precision?
Precision.
It's an interesting word.
Yes.
Maybe since this kind of more intro thing, we also say accuracy sometimes, right?
Right.
So and there's a difference.
Correct.
So what's that difference? Accuracy,
so the accuracy
precision.
is how good is your calibration.
Okay.
Right. The accuracy really depends on what is your set of standards that you have. How good is their value?
All right, and that's going to be a measure of, do you get the right number, right?
Correct.
All
and
right.
standards usually, I mean, certified reference materials have been measured with different ways and by different labs. Otherwise, they wouldn't be certified. And with the standardless program, right, that is depending on the algorithm that's being used and also how much was there to begin with to try out different things or to accommodate different modes, different samples, and so on. So accuracy means, if you think about it as a bullseye, how close to the center of it is it?
Okay.
Right? Whereas the precision is how close is several measurements to that hit in the bullseye. Or even if it's on the side, it might still be that you measure 10 times and it's always right off the same part.
All right, so Doug wanted to know, what about the precision? So I would say, what's the precision of something like this?
It also depends on what you're measuring, right? The more, in general, it comes down to how much intensity do you get out, right? Metals fluoresce a lot, so getting high precision on them, getting ppm level, or sometimes even a little bit below, is achievable. Whereas if you look at sodium or fluorine, trying to get to 1 ppm, you just won't be able to do that, or you have to measure super, super long, and that might kind of crisp your sample a little bit.
All right. So there's always that case, right? Any analytical technique, there's the best case scenario, best prepared sample, and then there's the deviation. So it sounds like it can be pretty darn precise if everything is right.
And the thing is, right, you can go to, in the same sample, to 100% iron with like a few ppm of chrominate or something like that, right?
And so how much does sample prep influence that precision?
Well, if your sample prep is repeatable, that's great. If it's not repeatable, like with my cookies, right? I don't have a very repeatable sample prep. Then your outcome differs.
Okay.
And it looks like the company that made these store-bought ones has a much better homogeneous batter available than I do.
They're very good at sample prep, right? The next person, so Chi wants to know, is there any interesting, weird, or notable things that you've seen? What's come through the door? What's your most...
So I think one thing, the feed and food stuff is actually pretty funny. Like, for example, you can measure if you get ground material, ground beef, ground meat, you can measure calcium and then you know how much bone was grounded with it. Right?
That's interesting.
That's kind of cool.
Yeah, I mean, because that's like one of those things where somebody would come to me and be like, well, how do I measure how much bone is in this? And I think from the first half, you're like, visually, how do you do it?
Yeah, because you wouldn't see it.
But you use calcium, huh?
Yeah, you can use calcium for that.
Really? Wow.
And staying in that same thing, I had a colleague who measured powder and like mixed with something and pre-made formula for babies because she wanted to know which one was better in the shortage around 2-3 years ago. And because she has access to a WD and an XRF system, she measured it and she saw that the one that she made with the powder, even according to the recipe, has more potassium in it and more calcium than the pre-made store-bought one.
There we go.
That's interesting.
So you can double check everybody out there. All right, so the next question, that's from Molly. Are there any branches that are not using XRF? Where would it make a lot of sense? So I think probably any areas where you think that we're not using XRF right now.
I think XRF is used pretty much everywhere.
Yeah.
It just depends on the degree, right? So plastic industry is using XRF, but they could maybe use it more, right?
Yeah.
The feed and food, as I just said, is working on it. I don't know. I think, battery is just starting up. We can't measure lithium. You will not find a commercially available
Yeah,
XRF
yeah.
system that can measure lithium, but we can measure all of the other elements that are in it.
Yeah, and I think one thing that's really changing that is something that we're seeing as an industrial trend in analytical. And that's the idea that it used to be that you had a specialist who had to run the machine, and then because it was so expensive, it had special requirements for maintenance, rooms, stuff like that. It had to be at a special place. In the university, you might have one in one department.
Yes.
But nowadays, these things are so easy, you can put them right next to your experiments,
Yes.
right next to the problem.
Yes, and I also like it when I work with universities, because
Yeah.
you get like a grad student who does this,
Yep.
and especially the ones with the shared departments, you get all kinds of different information and,
Yeah.
and problems that need to be solved. And it's a great it's great to be part of.
Yeah. Yeah, I mean, one thing that we used to do, so like when I was growing thin films, is we'd make the actual targets that we make the film out of. And so we'd mix some and stuff, but we never knew what's that composition after firing. Had to do some XRF on it. It was kind of annoying though, because we had to go. So I was like in the College of Engineering. We had to walk all the way over to geology and then run that there and get the composition. Man, it would have been so nice to have that, you know, if not in our lab, at least just centrally located a little bit closer. I think something like this would have worked great, because as a user, I could have just walked up, pressed a button, got my composition, and then gone and fixed my issue.
But we know geologists love XRF.
Oh, they do.
Yes,
I know.
they do.
I know. It's one of their core,
Yes.
their core things.
All
This
my
is under
colleagues
their
are
Christmas tree. right?
geologists. Yes, yes, that's on the Santa list for good geologists.
All right. Next question is from Mike. Is it dangerous to be next to the machine, or even in the same room?
No, it's not.
Okay. I was going to say, depending on the answer, I might be leaving. But
No, it's not. No, first of all, right, this is shielded. You
Yeah.
know when the X-rays
Yeah.
are on. It's also very low power. And if you remember what we looked at for the modes earlier, right,
Yep.
there was vacuum, helium, air. If I measure in air mode, I can't see light elements. And if
Yeah.
I'm far enough away, I won't be able to see anything.
Yeah.
So one of the things that you have to learn if you work with radiation, right, you have to go far away from the
Yep.
source.
Yep.
But yeah, this one, because it's shielded, even if it were open, it's
Yep.
not high enough power.
Yeah, and those machines at the doctor's office, they're using 300 kilovolts or so,
Yes,
much
that's
higher
different.
radiation. And like you said, that's going to kind of, you know,
But
be
it's
a
also
different
shorter
situation.
amounts of time.
That
right?
is true. That is true. So, but these things are super safe, not only on the radiation, but the mechanical side too.
Yes, yeah. We played a little bit with this machine so that we can show you how it moves. But
Yep.
usually, if I open the hood, this arm would not be moving, right? Because it's a moving part
Yep.
that should not bump into you while you're trying to do something.
Okay.
On the other hand, right, if you have one of these XY changers, it's kind of
Yep.
cool that while it's measuring, you can go in and like exchange samples, and you
Yep.
can mix and match. They don't all have to be solid. They don't all have to be measured in vacuum. You can have a liquid here,
Yep.
a powder there, and you can mix them all.
Yeah. And some of these machines, you can even have them externally loaded, right?
Yes.
I don't know if
you
it's
can have
this
like
one,
an yes, it does have
Oh, it does.
a thing
Okay.
in the back that you can connect it to automation.
All right. All right. Next question is from Diana. And why do you have so many different machines?
Why? Because
Why do you need that whole stable?
because I think it's important to, well, first of all, right, there's WD and ED
Okay.
XRF.
Yeah. So that's two machines.
That's two machines, right? There is a WD machine
Yep.
that is actually simultaneous
Yep.
instead of sequential. So it is even faster. So you put in one sample and it has like several goniometers or several channels
Yep.
around it. So that's for the extra fast people. That's our S8 Lion. The S8 Tiger is the WD system,
Yep.
right? Large chamber. Then we have the S6 Jaguar, which we talked about again earlier,
Yeah.
which is a benchtop WD
Yep.
XRF. So that allows you to get this like better resolution, especially for lighter elements, sodium, magnesium, but at a benchtop size,
Yeah.
right? It's for labs that don't have that much space, and also again a little more budget friendly.
Yeah.
And then when we get to ED XRF, we right now here have the system with the silver tube and the specific detector for light elements, but we do have a standard model too,
Yeah.
right? Yes, I'm talking about feed and food, but people who do like mining or people
Yep.
who do like this with the jewelry, they do not care about the sodium. In fact, the sodium that we would have measured off of this is me touching it, right?
Yeah, yeah.
So for that, a standard detector, a standard tube, which would be our palladium tube, is fine.
All right. So a whole bunch of different machines.
Yes.
And then the Last question that we have here. I have an EDS. Will XRF work for me? That's
Probably.
from Susan.
Probably. So the difference of those is,
Yeah.
right, what goes in.
Yeah,
right?
that's right.
EDS,
Yeah.
I mean, it also is energy dispersive spectroscopy. So,
Yeah.
I mean, I have to say the acronym is not very helpful, right?
Well, I think it's historical. I mean, because you had the systems, right? So
Yeah.
EDS are almost always on column on an SEM.
Yes.
But like you said, electrons in.
Yes,
And that's
electrons
quite
in.
limited compared to X-rays in.
Correct, because X-rays can go deeper into
Yeah.
your sample, whereas electrons would stay at the surface.
Yeah.
And because you have electrons, right, you have to measure in vacuum.
Yep.
If it's connected to an SEM, it's small, right? But here we can measure sizes. So this one is a 28 millimeter size. We can measure 34 millimeters. So it depends on what you want to measure. If you want to measure surfaces and very small, intricate parts, maybe not. Maybe an XRF mapping system would be great. Or if you want to measure like at the nano level, then yes, stick to your SEM. If you want to know what kind of overall material you have that you later then want to investigate the structure of, then yes, an XRF system would be great.
Yeah, and one other thing that sometimes people don't think about is that for EDS and SEM, the sample has to be somewhat conductive. And there are some solutions out there to solve that. You could coat it, or there's special SEMs. But if you get sample charging, that's a big issue. So things like the cookies and that might be an issue there. With XRF, you don't have that sample charging. So
I wonder what an SEM picture of a cookie would look like.
Really
Maybe we
tiny.
should ask our colleague here.
Yeah,
They just need crumbs.
Yeah, I mean, Bruker does offer actually EDS detectors, but like I said, right tool, right job. So there we go. So with that, I don't see any other questions. Let me just check here. Oh, here, we got one question here from Amir. Hello, I ask for Smart Matrix. It is quantitative application. Does that mean something to you?
Yes, so Smart Matrix is one of the default programs as well.
Yep.
And the matrix is CH2? Yes. So the matrix is an organic matrix. It's usually used for oil. The nice thing about this is with the software you can make your own smart method, so it will use the algorithms for the standardless program, but you can adjust it how you want to. You actually can do that with all of our software. So if you want to measure limestones, instead of measuring calcium oxide, you can set it to calcium carbonate.
Okay.
And instead of doing that painstakingly for every single sample, if you measure this very much, you make your smart limestone program, right? And so with the matrix, we offer this for oils, but you can change it and you can call it smart cellulose and set the matrix to cellulose, for example.
So I've seen before that you guys offer these kind of kits. You know, it'll be like, oh, the cement kit or this kit.
Right.
Is that kind of like this, where it helps you to set up for that method?
Yes, but with the cement kit, so these are what we call turnkey solutions.
Yes.
So you get the standards and then you can measure with them.
Okay.
Whereas the standardless program, you get the standardless program, and you can make adjustments on how you evaluate it.
Yep.
But you don't have access to the standards because that would be a little bit of an overkill. But if you want to set up a very large range calibration, by all means, get the standards. We will even give you some pointers on how to set it up.
All right, and one of the benefits then of that is that you have that whole expertise of the Bruker development team in terms of putting that method together. Speaking of methods, I know sometimes we talk about ASTM methods or these standard methods out in industry. Are these systems set up for those types of methods?
Yes. I mean, we do have experts sitting on some of these committees. And sometimes those systems are referenced, not use the S2 Puma, but use an EDXRF system. Right? So in the oil industry, ASTM D2622 that requires a WD system, right? When we make a new machine, we also test that they all pass, because it would make no sense to have a machine that doesn't pass very frequently used methods.
So this machine would be capable of something like that, like an oil test, something like that. Now, if I bought the machine with that, see, I'm going off script, I'm going to make you nervous. If we buy that machine for that method, and then let's say I have another problem that pops up, and I just want to get a spectrum. Since the EDXRF, it can give me that whole spectrum. Can I do that, or is it like locked in to only be able to measure the standard method? Okay.
You get
All
full
right.
control over your system.
Really? Okay, so that's a great benefit then, is that in one hand you get the standardized methods, but on the other hand,
Yes.
full capability to do whatever you
Yes.
need.
I mean, I really support
Yep.
customers every day. I
Yeah.
take calls, I email back, I try to
Yep.
be very responsive because I personally am very impatient. I don't like it
Yep.
if I have to wait, right?
Yep.
But our goal is that a customer who has this machine is self-sufficient, right?
Yep.
I mean, as a customer, I also wouldn't want to depend on that application person
Yeah.
replying to me, right? So it's kind of a balance. At the beginning, you might need a little more hand-holding, but later we want you to be self-sufficient, independent, and maybe just ask a question here and there if something new pops
Yeah.
up or you forgot how something works.
Yeah, that's one thing I know I always appreciated actually as a customer, just in general, is a company where like I buy this and then it's like if I have a problem, I just can call up, get an answer. It's not like the first thing that they say is, okay, what's your contract number, or what's your credit card number before I even talk to you.
That would take me way too long to find
Yeah.
that anyways.
So it's that's one thing I know I always appreciate as a customer was that application help. Yeah, of course, if it gets into like, we're deploying a new method and I need you to spend 4 hours online helping you, we offer that as a service, but yeah. So with that, we're going to sneak in this one from Tahir. Can we analyze industrial waste materials like sludge or catalyst contaminated soil?
Yes.
All right.
But
Yes.
it depends on what you want to measure, right?
Yeah.
I mean, what are the levels? But in general, yes.
All right.
Just tell me a little bit more about it, what exactly it is. So
Yeah.
if you want to measure soil and you want to see if there's, I don't know, cadmium in it,
Yep.
yes, you can measure that.
All right. So with that, we're going to kind of close out this session. Thank you, Julia, for joining us
Yes,
today.
thanks for having me and letting me place my system here in the studio and show it a little bit.
It's always nice to see these things and to learn a little bit more. And for everybody out there, thank you for spending your time watching. We really appreciate that. Hopefully you took a few little nuggets of information from this. Now, if you do have any questions that do pop up into your mind while you're watching this, you can always email them to live.events@bruker.com and we will get right back to you with an answer. Now, until next time, though, I'd like you to all keep your signal high and your background low.